to take a few minutes to put them up on Canvas, but here you have your assignment. Your first assignment's back. I saw a lot of really good work. If you want to make any improvements and change your score, you can do so. You have a week to do it. Hello. You have a week to do that, so if you want to submit rewrites, they're due a week from today. Your score can't go down. So if you do if it were to get lower, I'm not going to reduce your score. So you can try to get some points back if you want. And then we're working on assignment 2 as well. That's due on Thursday. Before we do new stuff, and I've got a new set of notes to hand out. Today's Tuesday, yeah? So I think we're gonna finish chapter 3 either a week from today, probably a week from today, I want to say. We're off on break the week of the 24th, I think. So my goal, and I think it's really attainable, it seems like reasonable, is on Thursday I'm going to hand out assignment 3 to get us working on some of this Boolean Algebra stuff that we're starting today, that you'll turn in on the 13th. On Tuesday, the 11th, I'll probably hand out the first test and the first assignment. So you'll still be working on assignment 3, which won't be super long or anything, but I want you to be able to get a little bit of feedback on that. The take-home test will be due on the 20th. That's a Thursday, and that'll be when we have our first in-class test. So I'm just going to go ahead and schedule it. We talked about it tentatively, but I'm just going to kind of carve it in stone. So we have a take-home test due, and we'll also be taking our in-class test. I will have a practice in-class test. You might have some questions in your minds right now about what to expect, and I promise that it'll be, I think, fairly clear when I hand that out. And then we'll have it done. I mean, you won't have to think about this stuff during break, but you totally could. Okay.
When's break?
I think it's the week of the 24th.
February?
Yeah. Okay, so we have that coming up. We're working on assignment 2. Any questions that folks want to ask before we jump into Boolean Algebra? Okay. Then I've got some notes for you guys. You have a variety of terms. Do they all write in the same part, or are those indicative of the color that you have? Okay.
Yeah. Wow, we got that. I have this. My proudest moment is Katie's. You stole it.
Are we ready? Y'all, this is pretty fun.
I did have a question, actually.
You
It's
did?
not related
Okay.
to math, though.
Oh, okay. Alright.
When I was uploading this using Cam Scanner,
Yeah.
I couldn't figure out how to rearrange it so the pages were in the proper order. Do you know how to do that?
Not off the top of my head, but I would be willing to look. I use Adobe Scan more than I use Cam Scanner.
Okay.
But I imagine they work on the same basic principles.
All right.
Okay. All right. So we just did, we spent time on chapter 1, which was on propositional logic. And then we'd spend some time on sets and, learn some properties of sets. And we had a lot of properties that kind of, I don't know if they felt to you like they were similar. They definitely kind of, even the notation that we use looks kind of similar to me. Like the similarity between the and symbol in propositional logic and the intersection symbol, which we even just call and in working with sets, right? The similarity between the or symbol and the symbol we use for unions with sets, and just these two properties, which are essentially the same. In propositional logic, we say that and distributes over or. In sets, we say, oh, the intersection distributes over the union. And as it turns out, propositional logic and set operations are just specific examples of a more abstract construct, which we call a Boolean algebra. So the first thing we'll do is just define a binary operation. A binary operation, if you have a set, you have some set. An operation is binary if you take two elements and combine them to make a third element of the set. Right? Binary means it takes two elements. You can also have unary operations, which is just an operation that acts on one element to produce another element of the set. So a Boolean algebra, you have to have a set and some operations. So we're going to use, so we're going to call this set B, but it could be whatever. So we have some set we're calling B. We have a couple of operations. Now we are writing these operations as times and plus, but don't think of them as the arithmetic that we know, the multiplication and addition of the integers. We just needed to pick some symbols, so we did.
There's only so many symbols to keep.
There's only so many symbols, yeah. So in order to be a Boolean algebra, we have these two binary operations, and these four axioms have to be true. First, both plus and times are commutative. So what does commutative mean?
Work over each other? No. It's associative, right?
It's distributive, I think.
Doesn't matter which one comes first.
Right. So plus is commutative, meaning that
A plus B is the same as B plus A.
yeah, and then times is commutative, means A times B is equal to B times A. So that's the first axiom. These operations have to be commutative. Next, we need a couple of special elements, and we're just calling them 0 and 1. Don't think of them as the 0 and 1 of the integers. As it turns out, it's not too hard to see that the integers are not a Boolean algebra. So we want to kind of get our heads out of arithmetic right now. But we have these special elements which we're calling 0 and 1, and they are the identity elements for addition and multiplication. And these look the way these will feel really similar. This feels like regular arithmetic. So the 0 element has to have the property that A plus 0 is always equal to A, no matter what element. If I can add 0 to anything, it won't change anything. And then times, the identity for multiplication, which is 1, has to have the property that if I can multiply any element by 1 and just get that element back. So far that feels normal, right? Next, each element has to have an associated special element, which we call the dual of the element or the complement of the element. So every element A, there's some special A complement or A dual. And that special element has to satisfy these criteria. If I add anything to its own complement, I always get 1. And at the same time, for that same complement, if I multiply anything by its own complement, I always get 0. And then last is the distributive property. Each operation distributes over the other. So that means that times distributes over plus, and that feels normal, like regular algebra. But also plus distributes over times, and that does not feel normal to write. Feels weird just writing it out. Just looking at this last axiom. This last axiom alone should be enough to convince us that the integers under regular addition and multiplication are not a Boolean algebra, because plus does not distribute over times in regular arithmetic. But Boolean algebras do exist. And the first thing we're going to do is convince ourselves that Boolean algebras exist by showing that working with sets, like if I have a set and I look at all the subsets of that set, how they interact with each other, if I define the operations as plus being a union and times being an intersection, we can see that how those set operations interact with each other forms a Boolean algebra. Whoops. Okay. So S is any old set, and what we're going to do is consider the power set of S. So all subsets of S. So an element of this set, of the power set, is going to be any old subset of S. We are defining, right, the operations are union and intersection. So union, that'll be our plus, and intersection is our times. So we're just going to show that the power set of S with these operations form a Boolean algebra. And to show that something forms a Boolean algebra, or that something is a Boolean algebra, we just have to show that those four axioms are satisfied. So the first one is to understand that union, all we really have to do is cite this as a fact. Union and intersection are commutative. These were properties that we learned in the last chapter. Right, A union B is the same as B union A, and A intersect B is the same as B intersect A. So that's done. What's the second axiom? Two special elements. So we need these two special elements. I'm going to scroll up just to look at that axiom and how it's stated. We need these two elements, 0 and 1, so that for any element, A plus 0 is equal to A. So in this, for this set, for this example, an element of our set is just some subset of S. So we'll take, say, a set A, right? That's a subset of S. If I rewrite like this equation using that notation, it would look like A unioned with something is always equal to A. Do we have a set, a special set, where that's always true?
A union with empty?
With empty, yeah. And so the other equation in that axiom says A times 1 is equal to A, so there has to be another special element, 1, such that, what would that look like? The times is so a set A intersect with some other set will always give you A, no matter what set A is. Like I could change the set A and it's always gonna, the universe, yeah, the universal set. So that means that the empty set is our 0 and the universe is our 1. So we have those special elements. Okay, axioms 1 and 2 are good. Axiom 3 says, for each element A and B, there is a special element, A dual or A complement, that satisfies those two equations highlighted in blue there. So for a set A, there needs to be a special set the dual or complement. We use, like we use the word complement in Boolean algebra. That's not a coincidence to what we call the complement of a set. So the dual element is A complement. So it has to be, I'm going to scroll up again just to look at one of those equations. A plus A complement is equal to 1, so that would look like A union A complement, and that does in fact always get me the universe, right? And if I take a set and intersect it with its complement, what do we get? The empty set, and that's the other equation that I highlighted in blue. A times A complement is 0. And then last we have the distributive properties, which I'm just going to write down. We've already gone over them in the last chapter. A union B intersect C is A union B intersect A union C, and then A intersect B union C is A intersect B union A intersect C. We've already observed those facts. So the sets, along with the operations of union and intersection and the special sets, in empty set and the universe, form a Boolean algebra. Boolean algebras exist. That's my point. Now we have other, so in any mathematical system, the axioms are the things that you kind of start with. They're part of a definition. You really just accept them as true. They don't need to be proven. Theorems, then, are what we prove. Theorems or lemmas or propositions, whatever. They're what we prove, starting with the axioms. So what we're going to do is prove a couple theorems. Before I do that, is anybody still writing, getting stuff on this page down, or are there any questions about what we've done so far? Okay. What color are you writing with now, Alan?
Switch to blue.
Blue, okay. Good. All right. So we have a pair of properties we call the idempotent properties. In a Boolean algebra, if you add any element to itself, you get itself. When I'm starting out proving a Boolean, we're going to sort of see how proving a theorem in Boolean algebra works. It's usually really streamlined. There's not a lot of writing, like in English words. Usually it's just a string of equals, like using axioms, which, you know, this equals this, which equals this, which equals this, bam, we're done. Like, it's really kind of pretty smooth. It can be challenging, right, trying to figure out how to get there, but there's not a lot of, like, writing that we have to do. It can be pretty challenging. I often first start, like, try to put it in context, get myself to the point where I can be like, oh, yeah, that makes sense, that should be true, by thinking about it in terms of set theory. So we're going to show that this is true for any Boolean algebra. A plus A is equal to A. But what does that equation look like if I'm talking about sets?
Repeat the question.
So this equation that we're going to prove, right? Yeah. What does that look like if I try to translate it into the particular Boolean algebra where I'm working with sets like we were just working with on this page here? If I translate that into set theory.
A union A plus empty set.
Say that again?
A union empty set is.
Where does empty set come from in that equation? So what is the empty set in a Boolean algebra?
Set that doesn't contain anything.
Right. It's our zero element. So if I'm taking a Boolean algebra in a Boolean algebra equation and I'm translating to what it would look like in set theory.
Maybe A intersect A is A.
Close, except plus isn't intersect. It's union. So this would be saying if I take a set and union it with itself, I just get itself. That seems true. We're going to show that it's true for every Boolean algebra. So here's how we do it. A equals. Now I'm going to use some axioms to rewrite this. I'm going to have like a nice string, continuous, maintaining equality all throughout. And at the very end of it, I'm going to be able to write equals A plus A. And then the stuff on the very left that we start with and the stuff on the very right that we end with, those have to be equal. So often a Boolean algebra proof works, like the way we get it to work is to work in an identity element somehow and then use the complement laws. So I'm going to say A is equal to A plus 0. This is axiom 2. I'm going to give a little reason. Anything plus 0 is itself. And now that I've got 0 worked in there, I'm going to use that third axiom that deals with complements. So that third axiom says if I times anything by its complement, I get 0. So I can rewrite 0 as A times A complement. So this is axiom 3. This next step we're going to take is a little bit tricky. Because it's not as obvious. We're going to use the distributive property. How am I going to use it? And I guess I should have parentheses here. But
A plus A dot A plus A complement is.
yeah. So this is axiom 4, because this is the one that feels weird because it's not true generally in arithmetic, but plus distributes over times in a Boolean algebra.
Who decided that?
Just, just part of the definition.
Mathematicians can play whatever games they want, as long as everybody agrees on the rules.
Right? Or like somebody says, here's some rules, and then, whether or not people kind of decide to play by those rules ends up, I think, being a function of how interesting the results are when you start from those definitions, or how useful those results are. Now I'm starting to get excited here. I'm starting to feel good about this proof because, first of all, I see the expression A plus A at least involved. Right? And I want to keep my eye on the ball. We're hoping that we're going to be able to show that A is equal to A plus A. What about this part here? What can I do with that?
That becomes our one.
That's a universal
right?
set.
Yeah, which is 1. Yep. So, so this is A plus A times 1. And what axiom is that?
Number 2.
Where do we see that in number 2?
Oh, it's an axiom 3.
Yeah, right here. Axiom 3 is the one that's all about complements.
Yeah.
Axiom 2 just talks about the existence of the identities and what they mean. So this is axiom 3.
So wait, are we doing with the complement of A?
What's that? And you want me to go back up to the axiom?
Yeah, because this one says A plus A times 1.
Well, right. So we're using axiom 3. Axiom 3 is how we get from here to here. Axiom 3 is what says that if I add anything to its complement, I always get 1.
Oh, I see.
And now what are we going to do?
Get rid of the 1,
How?
put a 1 on the other side.
We're not working on both sides of an equation.
Anything is times with 1 is the same thing.
Okay, so what axiom are we using? That one's using number 2. Yeah, number 2 is all about the identity elements and what they mean. So 1 is defined to be the element such that if I multiply anything by 1, I don't change it. So whatever A plus A is, I times it by 1. I just get A plus A. So now look at this. Look what we did. We started with A equals. We maintained equality throughout and then ended on A plus A. That means that what we started with, A, has to be equal to A plus A, and we're pretty much done. How's that?
I like that a lot more than writing the other proofs.
Well, don't worry, we'll get back to those proofs. But
Okay. Fun. Like,
you'll get to do plenty of these too. There's a few in the practice exercises, and there will be probably one or two that show up on the next assignment. Okay, now we're going to prove the other idempotent property. We're going to show that if I multiply anything by itself, I just get itself. And again, if we start similarly, like, what does that equation look like if I rewrite it with sets?
This time it's going to be intersect, right?
Yeah. If I intersect anything with itself, I just get itself. Pretty sweet. Passes the I believe it phase. So
The
let's-
narrative phase.
yes. All right. This proof will go pretty similarly. I'm going to start with the element A and rewrite it. The last time we rewrote it by working in one of the identity elements. By saying, oh, I could take anything, it's the same as itself plus 0. I'm going to take a pretty similar step, but not exactly the same. And I'm going to rewrite this as A times 1. Again, I'm just using axiom 2. Anything times 1 is equal to itself. And I wanted to rewrite it with an identity element because that's what lets me use axiom 3 to rewrite that identity element using, complement. So 1 is, I can always replace 1 with anything plus its own complement. So I could replace 1 with A plus A complement. I could replace 1 with B plus B complement or C plus C complement. I'm sticking with A because this Boolean algebra equation only deals with one element, A. So I'm picking that one because it's what's going to be helpful. So this is A plus A complement. This is axiom 3. A plus A complement equals A for any element. Now what can we do? We can distribute. This is the distribution that feels normal, right? Times distributes over plus. So we have A times A plus A times A complement. And we're starting to feel pretty good because we see the product A times A at least show up, and that, it's what we hope our final result is. So this is axiom 4, and this time we're using the fact that times distributes over plus. What now?
A times the complement equals 0.
Yep, and what axiom?
That is axiom 3.
Yeah, so axiom 3, axiom 3 is the only one that deals with complements.
Axiom 2 is the cool one.
Axiom 1 is about the existence of those identity elements. So this is axiom 3. Anything times its own complement is equal to 0. Now what?
Just A times A.
Yeah, right, so we just get A times A. And what axiom is that, Zach? Axiom 2.
is that you?
Times A.
Wait, was it not Zach that said that?
No, I said it.
Okay.
Yeah, I said it.
Yeah, their voices sound very similar.
I just know that you're in that side of the room right now, and I wasn't looking. So axiom, what was it? Axiom 2? A plus 0 equals A. So again, we started with A equals, we maintained equality throughout, ended with equals A plus A. So what two things are equal here? A, yeah. Mm-hmm. Or, you know, feel free to make up your own catchphrase if as desired feels tiresome. That's fine.
Make it so.
Make it so.
Make it so. As you wish.
Mm-hmm.
How many references can we get?
These, there's got to be a Twin Peaks reference we can make, but these two theorems look similar. One is A plus A equals A. The other one's A times A equals A. There are other examples of this where you have one theorem, which really just a theorem in Boolean algebra comes in the form of an equation, where one equation is true and you make some adjustments, very routine, like methodical adjustments, and you can like come up with another equation that's got to be true and can be proven in much the same way. These proofs are almost identical. If you look at the axioms, each axiom kind of comes in the form of a pair of equations, right? Here's an equation for plus being commutative. Here's an equation for times being commutative. Here's an equation that defines the 0 element. Here's the equation that defines the 1 element. Here's an equation that defines how an element combines under addition with its complement. Here's an equation that defines how an element combines with its complement under multiplication. Here's times distributes over plus. Here's every axiom is a pair of equations. Okay. Now look at these proofs that we did. Oops. Axiom 2, 3, 4, 3, 2. Scroll down. Axioms 2, 3, 4, 3, 2. And if you go line by line, we just use the other equation of the same axiom each time. So these two theorems that we proved are so similar, we say that theorem 2 is the dual of theorem 1. So we have dual of elements, we also have a dual of theorems. And you get the dual of a theorem by interchanging plus and times, like wherever you see a plus, write a times, wherever you see a times, write a plus, and interchanging zeros and ones. That's basically it. And if you've proven one theorem, that means you basically have the proof for the other one. You just kind of have to switch around which equations you use. Yeah.
So if I would like to, like let's say I'm doing a bigger proof that ends up using the idea that A equals A plus A,
Mm-hmm.
can I just say that, or do I have to go step by step?
Oh no! If you want to use, so we just proved it right now. We don't unless you're doing something and the instructions say use only the axioms to prove this. Then use these results. We just did some work to prove a couple of results, and unless you're instructed otherwise, you may feel free to use the fact that A plus A is equal to A, and use the fact that A times A is equal to A. Just say, like we proved in class, or by theorem 1 or by theorem 2.
So are these generally known as theorem 1, theorem 2?
No. In fact, that's always the case in any math book. In mathematics publications, they start numbering at 1, every publication.
Okay.
They are all called the idempotent properties.
Okay.
Yeah. Yes.
Go back up one page,
Up here?
down a little bit, to the bottom of the
Down
page.
here?
Oh, I think I'm on the wrong one.
Right there.
It's page 31 of Boolean Algebra.
Page 32.
What? What?
With the special elements. Yeah, this one down the bottom of this page.
It's there.
What?
Yeah.
I don't understand.
Never mind. I'm getting confused.
So the special, like the 0 and 1 elements for the sets. So in this, at the bottom of this page, we're working through the example, like sets,
Comparing them to...
and seeing how they are a Boolean algebra under union and addition.
All right.
And here we identified what the special elements 0 and 1 are. So our 0 element is the empty set, and our 1 element is the universal set. So here we have some more theorems. We're not proving them, but we could certainly write down their duals. Theorem 3 says if I take any element and I add 1, I get 1. That makes sense because if I take any set and I union it with the universe, I get the universe, right? So like that's what that would be in the particular instance of set theory. What is its dual equation? A times 0 equals 0. And what would that equation look like with sets?
Intersect empty set equals empty set.
Mm-hmm. And that makes sense, right? Seems like that should be true. The theorem 4 and its dual that we're about to write down are referred to as the absorption laws. A plus A times B is always equal to A. What does the dual look like?
Times A plus B equals A?
A times A plus B equals A. Yeah, whoops, not 0, equals A. So there was no zeros or ones to interchange, just the plus and times. Before we go on to theorem 5.
What did you say that was, the absorption?
Absorption, yeah. So we can, if we look at the absorption laws and what they look like for sets, the first part, the part on the left, the one that was given, that would look like A unioned with A intersect B is equal to A. I think we can convince ourselves this should be true looking at a Venn diagram. So this says I'm going to take all of A and then I'm going to union it with just the intersection. And that should equal A. So with the union, anything that's shaded at least once gets included. So clearly, like the part that's shaded is just A. Like if I take a set A and I union it with A intersect anything, it's just going to give me A. I don't add anything new. The other side, the other equation was A intersect with A union B. And if we draw that as a Venn diagram, overall what we're going to do is find the intersection of A with some stuff. So here's A again. And then we're intersecting that with A union B. And with an intersection, you need, it's the stuff that we've shaded twice, right? So that still ends up being just A. Actually, before I scroll down, questions on that?
See, that's when his multicolored pencils come in handy.
Mm-hmm.
You can see we shaded twice.
The other thing, cross-hatching works too.
Okay.
Like making them go the other direction is good. Okay, associative properties. Addition is associative. Guess what? So is multiplication. If I have A times B times C, that's the same as A times B times C. It doesn't matter if I do A times B first and then times C, or if I do B times C first and then times A. That's associativity. Theorem 6, this says that the dual of A dual is A, or the complement of A complement is A. What is that dual equation?
Is there one?
It is itself. There's no plus and times interchange. There's no zeros and ones to interchange. We would say that that theorem is itself dual. Theorem 7 says the complement of 0 is 1. What's its dual? Complement of 1 is 0. And then, here we go. We all knew this was coming, I think. De Morgan's laws. De Morgan shows up in logic. It shows up in sets. So, you know.
Who invites the guy? Come on.
Yeah, right?
It's a party crasher.
So, De Morgan, in this, the first equation says the complement of A times B is A complement plus B complement. What is its dual? No, oh, hold on. We're getting ahead of ourselves here.
A plus B in parentheses, then the complement on those
Mhm.
equals A complement times B complement.
Yeah, there we go. Thanks, Zach.
No problem.
See, I did that one on purpose. How's that?
That part's easy.
Good. Good. Okay, fun?
Wouldn't say that.
It's not bad.
I'll say it for you.
Okay.
Yeah.
I'll say it.
It's just more of what we already did, it seems like, with different symbols.
Yeah, and it's just, we're kind of abstracting it. Like, one of the things that made Boolean algebra hard for me at first was just thinking of plus and like getting myself out of the habit of thinking addition and multiplication, right? And once I learned that I could think of it, like bring everything back to sets to kind of contextualize it, everything got so much easier. So, so now we have another, so there's, Venn diagrams are one way, contextualize it with sets, and you can kind of visualize it with Venn diagrams. We have another way to kind of represent these Boolean algebra expressions. And that is to create a combinatorial circuit or a logic circuit, also called a Boolean circuit. But we're going to draw these circuits that represent. Yeah. Did you have a question, Mukti, or were you just? Oh, okay, good. So we have some inputs. And, there's very like digital circuits or digital whatever, like digital expressions. You have some inputs that are either 0 or 1, or they're either on or off. With sets, an element is either in a set or it's not in the set. With a proposition, it's either true or it's false. So there's a lot of overlap here in what we've been looking at in the first couple chapters. So we have 3 basic types of gates. We've got an AND gate, an OR gate, or a NOT gate. There's another gate that we're going to construct in a little bit. So we can see what a gate will do. I meant to include this line here. By essentially defining it in the truth table form, right?
I was going to say that.
So, yeah. Here's the AND gate. The AND gate is curved here. And it does exactly what the AND does for propositions. If they're both off, the whole thing's off. If at least one of them is off, the whole thing's off. It's only on when they're both on, right? It's only 1 when they're both 1. This is just like with an AND operator with propositions. You only get a true if they're both true. So the AND gate is just like the AND for propositions, just like an intersection for sets. In order to be in the intersection, they have to be on. You have to be in both sets. The OR gate looks more like an arrowhead there. And for the OR to be true, or to be on, or to be 1, or whatever, you need just at least one of these to be on, to be 1. So the only time this gets a 0 is if they're both 0, just like with an OR with propositions. The only time you get a false is if they're both false. And then the NOT gate is only 1 in and 1 out. It just negates what your input was. Just like a negation of a proposition, just like the complement of a set. Unsurprisingly, we represent the output of an OR gate with addition. So if my inputs are A and B, the out of A or B is, we just write it as A plus B.
Y.
What's that?
On the previous page it was Y.
Yeah, well, it would be A plus B is Y. Whatever that output is. If it's passing through an OR gate, we call it A plus B. If it's passing through an AND gate, we call that output A times B. And if it's passing through the NOT gate, we call it A NOT or A complement. So we're going to draw a circuit for this. Are we excited?
No. I'm kind of excited. I
Good.
kind of remember doing this at one point.
Okay.
It was probably with you.
Oh, maybe. Yeah, yep. How many inputs do we need?
2? No.
We need 3 individual ones. In the end, we're going to be passing. So you might be picking up on the fact that, I'm adding a couple things together, right? We need 3 inputs because I have an A and a B and a C. But in the end, like I know what the end of this circuit is going to look like. I'm going to pass 2 things through an OR gate, right? But I got to kind of build that up. So I got to, A, obviously one of those things is just plain old A, and that'll be pretty easy. But I got to build the other thing to pass through the OR gate. So let's begin. I'm going to have, here's A, here's B, here's C. And I'm going to start by constructing this. And I always start on the inside and work my way out. So what I need to do, there we are. What we need to do is pass C through a NOT gate. And then, so let's do that first. Here's the NOT gate. So there's C naught, and then it needs to be multiplied by B times B. So, which is an AND gate. So I'm going to take the C naught and pass that through an AND gate with B. So right here, and if you want, you can make a little note. It can be helpful. What's coming out of that AND gate is B, C naught. What do we do now? What needs to happen next? Yeah, because we got to take care of that negation right there. So there's that. Now what's left? Yeah, so and this is A plus BC naught. The number of gates you need to use in your drawing usually corresponds to the number of operations you see. Sometimes you can use a gate twice in a drawing, in a circuit, so that isn't always absolutely true, but a lot of the time it is. So you'll note that if I count up operations, including the negations, I've got 1, 2, 3, 4, and I've got 1, 2, 3, 4 gates.
Say that one more time.
So usually, sometimes we can use a gate like twice for more than one thing. So I'm not going to say that this is true 100% of the time, but usually, then if I count up the operations in the expression that we start with, so I count up how many plus, times, and nots. Just count them all up. So here's 1, 2, 3, 4.
That's how many gates.
That's how many gates. Yep. Let's go the other way around.
Looks very similar to the one we just did.
Yeah, it does look kind of similar. At the end, we are just going to be adding a couple of things, right? Because that's the very last gate. One of the first things I do when I go through is I just write plus and times in, because sometimes people, sometimes we forget which gate is which, and this just helps me keep track. So there's a plus, times, and times. And of course, usually the negations are easy, so I don't need to worry about marking those, but you can do that too.
You can write the outputs, right?
Yeah, write the output. So let me zoom in to get some more space. Let's start on the left. Start at the beginning. If you're going in this direction, if you're starting with the circuit and want the expression, start on the very left. Build out what's coming out of each gate from the left onward. So what's coming out of this knot?
Not C.
Yep. And then what about this gate here?
BC naught. BC naught.
Mm-hmm. And how about up here?
AB.
AB.
Is it?
AB not.
AB in parentheses, not. Yep. And then what about this?
BC not and AB in parentheses not or.
So BC naught plus AB naught. That's it. That's what we wanted.
When you're writing the final step, does it matter which one goes first?
Oh, no, because addition is commutative. Yep. Griffin, you're being too loud.
I'll just absorb this one.
I'm having a fun time picking on Griffin today. Has anybody noticed that? I don't know why, but
It
sorry.
makes it so
Really
easy.
entertaining to do so.
Yeah.
Yeah, I love being different. Need some water?
If you have, if anybody gets sick, you know, you can wear a mask or something.
Coronavirus.
Yeah. Yeah.
East Coast.
It is now 11 cases in
Virus.
the U.S.
Well, prime, I'm glad it's a prime number.
Experts worry about pandemic.
Yeah.
It was like 8 yesterday.
8 is not prime. Well, it went to the next highest prime. Like, what else was it gonna do?
Nothing ever happens in Vermont, so I'm not worried.
What's that?
Nothing ever happens in Vermont.
Yeah. Okay, so let's do another one.
What a circuit.
What? Yeah, what a circuit. So look, if two lines cross in a circuit, that doesn't mean that it necessarily splits the output unless a node is drawn. So here, C is being split into these three gates, into this not up here, into this and, or into this or, and into this and at the bottom, because there's a little node. There's a little node here, right? Whatever's coming out here is getting sent to this and to that. There's no node drawn here. So that's just, those lines have to cross.
So you would start at the node in this case?
I always start in the beginning. I start in the leftmost gates, track what's coming out of each gate, and then kind of build it up the way we did in the last one. There's just more going on here. So let's start. I'm going to actually mark out the operations. So we have plus, not, plus, times, plus, plus. Okay, let's start. What's coming out of this plus, this OR gate at the bottom?
You see?
B plus C, right?
Yeah.
And then we have a little not gate. What's coming out of that?
See that?
C not. And this next plus OR gate?
AC?
A C naught. A plus C naught.
A plus C not. Yeah, it's a plus. Okay, now let's do these three AND gates. Let's start at the top. Top one?
Doesn't take that. Takes the A.
It's A plus, or
A.
it's A, B, C.
A times parentheses.
That's what
A times parentheses. What's in the parentheses?
B plus.
B plus C, right? Because the other thing that's moving through that is what's coming out of that gate at the OR gate at the bottom. What about this, the middle AND gate?
A plus C naught times B.
Mm-hmm. The bottom AND gate? Say that louder. BC. Yep, B times C. Yep, good. Okay, we're almost there. What about this next OR gate?
A plus C naught times B plus BC. Oh, not that one. Sorry. Wait, what?
This one right here. What's
Yeah. Okay. So is it A plus C naught times B plus BC?
Oh yeah. So hold on. A plus, yep, and then plus what?
Plus BC.
Yeah, good. And then what's coming out at the end?
You do what's you got at the bottom one, the one you just did, all in parentheses, plus A times B plus C in parentheses.
And, you know, you said all in parentheses like that, which is true. You could write it that way. We don't have to include those parentheses because it's associative, actually. Yeah, the grouping of addition doesn't matter. So this right here, this is the unsimplified expression. That seems awful. And the circuit looks like a mess. So we have these properties, these theorems and axioms and Boolean algebra that we can use to simplify this expression. So we're going to do that next. And then once we get the simplified expression, let's draw the circuit for that. So we have I'm gonna write it in this order: A times B plus C plus BC plus B times A plus C naught. We're just going to use the properties and theorems. We don't have to write like a proof. We're just going to, any of the axioms or theorems from the last section, we're just going to use to rewrite this. We might cite reasons, right? That's always a good idea. So, there's probably more than one way we could start this, but I'm going to start by focusing on this part, and in particular, the fact that we've got a common factor of B. I don't want to abuse that term too much because it doesn't necessarily mean the same thing, but we can use the distributive property in reverse. I could think of that stuff in the red box there as being the result of having distributed B times over an addition of things. So the first term I'll just bring right down, B plus C. The distributive property works in both directions, right? I could think of it as distributing something through, or I could think of it as taking something out. So if I think of the stuff in the red box as having distributed a factor of B through an expression with addition, it would be C plus and then A plus C complement. And that is the distributive property. The next thing I'll do is use the fact that addition is commutative. So if I look at those parentheses at the end, first, actually, let me stop there. Questions on why these two lines are equal? Essentially, if I use the distributive property here, I could say B times that plus B times that, right? And that would give us that. So now, I'm going to use the fact that addition is commutative. And I'm going to rewrite the stuff in the last set of parentheses. I'm still just going to leave this A times B plus C as is. But I'm going to write this second set of parentheses, that stuff as A plus C complement. And I'm doing that so I could focus on that part right there. Do we know what C plus C complement is, Alan?
It's a 1.
It's a 1. And now let's look at this part here. A plus 1. What should that be? What? Did 1? Ah, that I didn't do on purpose. Something. Zach must be doing something. So Griffin says that A plus 1 is equal to 1. He's right.
Good job, Zach.
Griffin, why can't you be more like Zach?
Yeah,
No.
And then B intersect 1 will be, B.
Yeah, exactly. Okay, let me get my reasons in here. A plus 1 is equal to 1. And then you just said B times 1 is equal to B. Good. Okay, so now we have A times B plus C plus B. So we're not quite done yet, although it's already looking better, right?
Yeah.
We could do better, though. I'm going to distribute the A. And you know what I'm going to do? I'm sorry, this is going to feel like I'm undoing some work. I'm going to rewrite B as B times 1 again. And I'm gonna rearrange the order. I'm gonna use the fact that addition is commutative again. So I'm gonna have A times B plus 1 times B plus A times C. And now I'm gonna focus on just those two products there. What can we do?
Yeah, those equal B. Because if you're having the intersect of B and A, you're only going to have terms that are also in B, and same with B and 1, they have to be B alone.
But is it all of B?
No,
Yeah, let's use properties. So I like where you're going with that. And in fact, you could kind of do A times B plus B and apply an absorption law, but we can see why this is true, actually, just relying on the axioms. So think of that as the result of having distributed something.
B times A plus 1.
B times A plus 1. What's A plus 1?
A?
A times 1 is A.
it's 1 because
It's
the
1.
union of 1 and A.
It's the unit, yeah, if I take A and union it with the universe, yeah. So this is B times 1 plus AC, and so that's just B plus AC. We did make it better. How many gates?
This would be 2.
2. 1 for this times, A times C, and then addition. Whew. Sweet. Okay, let's draw this circuit. So I know it's going to end by just passing a couple things through an OR gate. One of them is just B. The other one is A times C. So here's A, and see that got to go through an AND gate, and then this goes through an OR gate. Here's the simplified circuit. This is why we call it simplifying. The first circuit looks like a Rube Goldberg machine, like in comparison. We needed only 2 gates to accomplish what up top, I'm going to scroll up briefly, I'll come right back down. Up top we needed 1, 2, 3, 4, 5, 6, 7, 8 gates. And we could produce precisely the same outputs for every set of inputs with only 2 gates. And we were able to see how it's simplified by using the Boolean properties, right? So that Boolean algebra was nice. It allowed us to get a simplified circuit.
Is this what bug fixing code looks like?
I don't know. I don't program, but
No,
if
no,
it
no.
that would be fun. No?
Not at all.
Okay, never mind.
Maybe bug fixing a circuit. These are like circuit boards.
Yeah.
Pretty simple circuit board.
I think bug fixing code is a lot to do with like searching for semicolons or something. How's that? Pretty good? All right.
Now we
Good.
know these 2.
What's that?
I looked at the last page.
Oh yeah. We're gonna do some stuff in the next section. We'll do that on Thursday. We'll do some, what's next? Binary arithmetic? Is that what's next?
Yeah,
Binary arithmetic and then constructing adders, which, will kind of come back to some of this circuit stuff. It's pretty fun. If you have questions on feedback that you got on your assignment, just let me know. If you have questions on assignment 2, we're getting ready to turn that in on Thursday. Let me know. I've got a help session tomorrow from 12:30 to 2. Good. Enjoy the rest of your day.
When is the resubmit due?
Thursday.
Tuesday the 11th. You always have 1 week from when I hand it back in class.
Oh, okay.